All right, welcome back. One of your Tree, have you worked through all those documents already? Have you watched all that stuff? So Tree was just saying that he found a good open source resource online, which is an introduction to MATLAB through MIT coursework. So if I literally just went to coursework, open courseware, sorry, and then I just clicked up here, MATLAB, and then went down here. So it looks like this was taught in 2011, and there's some nice video lectures on the topics, etc. At some point, I hope that my stuff is complete enough that, like, we've already done a little bit of this, right? We've done scripts and function files, we've done using files, we've done an introduction, we've done the command prompt. We will very soon finish up plotting in Lab 4. I think Lab 5, we're going to have a choice between numerical analysis. Like, there's this really nice root finding. I have a full lecture and lab associated with Newton's method that we could write up. But I will say that it is nice to have other resources. Over the weekend, I found some other stuff that I've been using to figure out how plot works at a very deep level. And I'll share that with you. But that's, apparently Tree found that. I don't know. It would be really nice if you wanted to, like, go through all that material and then, like, report back. Because sometimes if you don't actually go through it, it's not clear how good it is, right? Okay. So let's go ahead and refer back. I will say, though, that you will have a pretty decent introduction to MATLAB. It's not going to be, 7 quarters worth of development, because this is number 2, but you all will know what script files are, you're going to know what function files are, you'll know how to write code, you'll know how to use if statements. I'm not against that, right? And then you also have a very deep understanding of the numeric data classes. So I think you will do well, especially if you decide that this is something you want to do for yourself in the future. All right, so we had this concept that every binary 8 number we could think about as a sign, implicit leading part. So the thing that's not actually written, the significant and the biased exponent value. And when we thought about this, remember we had this concept of a raw bit string, right? And this will come back to us later. So how many total bits are dedicated to this data class? 8. And we said that our sign bit is the first one. And literally this follows the exact same pattern as what we saw in signed magnitude. And then we've got these 3 bits that store what we call the exponent. And then we've got the trailing bits that store the significand, or the fractional part. And I think we said, like, green for this, right? Right now I want to be a little careful, because earlier I actually said that the green stored E, but the green doesn't actually store E, it's going to store what we call U. The value of E is then calculated from U using a bias. And we're going to talk about that again in just a second. And then we've got this thing that we call the significand, and that was the last 3 digits here. So let me ask you this. Can you run through all possible bit strings in 3 unsigned integers? So what would be the 3 binary bits? So what's the least value that those first 3 could take? 0, 0, 0. What's the corresponding unsigned decimal number associated with that? 0. Okay. We're going to go ahead and mark these off. We'll talk about why we're going to do this in a second. So that first one is really, really special. Okay, what's the next bit string? 0, 0, 1, and then what? 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. We're also going to mark off that last one here. We'll talk about why we do that as we get further into this data class. Okay, what are the corresponding decimal representations of each of those? 1, 2, 3, 4, 5, 6, 7. This is the actual string of bits stored in memory. And then what we said was that the calculated value of the exponent was in excess 3 biased, which means that I take each string of bits and do what to it? Subtract 3. So if I wanted to know what the interpreted value of 0, 0, 0 was, well, that's 0 minus 3. So what we say is that the exponent value is u minus k. In this case, k is 3 because it's excess 3. Where they got this notation, I'm not sure, but this would be 0 minus 3. So if I have the bit string 0, 0, 0, what is the corresponding exponent value stored there? Negative 3. What's the exponent value stored if I have the bit string 0, 0, 1? Negative 2. And then what? Well, negative 3, negative 2, negative 1, 0. And then we're going to see that there's something called subnormal numbers and overflow. So these two, this is what we call subnormal. We'll talk more about that in a bit. What did we say a normalized number was?
1.
Normalized numbers always have an implicit value of 1 in front, right?
Right.
So any time that the exponent field is 0, 0, 0, we're going to see that we actually don't put the number 1 in front there. There's that implicit 1 disappears, and so we call that subnormal. It's below normal, right? We'll talk more about that. And then this is what we would call overflow. And some people say NaN. Do you know what NaN means? Not a number. So if your exponent bit goes above the 6 value, IEEE has a very, very specific way of dealing with that, which is to say that that's overflow in the data class, and we're done with it. Did I see a question somewhere? Yeah.
It's kind of like a not as clean way to do.
Yeah, I think that the reason that they did bias notation has to do with the concept of so when we actually do addition and subtraction, what will happen is if you add two numbers that whose exponent values are different, what they'll do is they'll increment the exponent number until the two exponents are the same, right? And then every time they increment, they'll shift the significand left or right depending on how they're incrementing it. And I think that it's a lot easier to do a bit comparison with non-2's complements numbers because you're literally just looking at values, right? Whereas in 2's, I mean, I don't know if this is true, but that's my immediate, without thinking about it for a few minutes and researching it, that's the first thing that comes into me, for me. In 2's complement, you're actually you would actually have to do a different type of incrementation based on that leading bit. But in bias notation, the order is maintained. So this order is identical to the order of the unsigned integer representation. And from that standpoint, if anytime you're doing addition or subtraction, you could literally just do a comparison and then increment it and decrement it accordingly, right? So that's my immediate answer. I'm sure there's a better answer than that one, but that's the one that comes to my mind immediately. Okay, so the next thing that I want to do Yeah, why don't I have you do this? So let me have you write, so these are some examples for you. We'll call it 6.6. So in code, the number 13, and then why don't we do some other ones as well? Why don't we do, I don't know. Yeah, let's do the number 1. And all right, so I want you to encode those 3 numbers in binary 8. And I'll let you choose which of those 3 you want me to do by hand. I'll do it for you. And then I'll share with you some other cool resources. We should put like a negative up on one of those, huh?
You can do -1.
Negative one? Okay. Yeah, let's put negative one. Let's make it a little more interesting. Okay. Anybody else get those? Yeah? All right. So what I wanted to show you next was the following. I haven't thought about having you all make a table in MATLAB to do this, though that would be kind of a fun activity. I don't think I'm going to do that this quarter. So one of the things that's really kind of brutal about the 16, 32, and 64 is that there's 2 to the 64 different versions, right? But 2 to the 8 is actually not that big of a number. What's 2 to the 8? 256, right? So at one point, when I was studying this way back when, I recognized like the Cleve-Moeller thing didn't happen until 2018. I was thinking in like 2010 when I was first thinking about this that it would be super helpful if I was studying this for the first time to get a sense of what's happening in norms if I could do it in 8 bits. So in your lecture notes, there's every single possible 8-bit floating point number that exists in this data class. Brought to you by yours truly. This took about 2 hours in LaTeX, so I did not do this in MATLAB. Although that would be a fun activity. And I also didn't do it by for loops. For loops would have taken me probably 10 hours. I could do it for sure. But I wanted to show you some kind of interesting features. So let's go ahead and look at. So do you remember we said this? What's the lowest value that actually makes sense in terms of a normalized floating point number? What's the lowest value of the exponent bit? 1. Yeah. So this set right here, this set of exponent bits, we call normalized. So right in that sweet spot. These are what we call normalized floating point numbers. And that has a very, very special meaning. It means that anytime I represent the binary 8 data class as a corresponding decimal value, what is the leading bit that is always implied but never written? 1. What's interesting about that is that it means that we extend the data class by 1 extra bit. So the really interesting thing about that is right now this number only has 4 bits in the significand, but the fact that these are normalized means we get a 5th bit for free, which is kind of interesting. So it increases the precision of our data by 1 extra bit. And then what I want to say is that when we have this, so if we look at y equal to this raw bit string, B7, B6, B5, B4, B3, B2, B1, B0, we're going to call this -1 to the B7 times, kind of a nasty looking notation, so -1 to the S times 4 normalized numbers normalized means literally that the exponent code or the exponent field is between these values. So if it drops down to 0, we'll talk about that in just a second, which is subnormal. And then literally this set of bits, so in this case we have -1 to the sign bit plus 1 point B -1, B -2, B -3, B -4 times to whatever the unsigned exponent field is minus our excess k value, and in this case the excess k is 3. So if you're actually thinking about the representation of what that thing is in terms of its map, this is it. If, on the other hand, u is 0, 0, 0, then we are not normalized. So what's crazy about this is, if it's the case that that the bit string that I actually store in memory is 0, 0, 0, the corresponding number that I get out, this first digit will go to 0, and it becomes literally a fixed point data class. So the moment I know this is 0, what is the corresponding value of -3? Of exponent? Always -3. And what's crazy about this, you got to actually get into this a little bit, but we'll do this as a team right now. A lot going on that table. Yeah. So check out this. Let's focus in just on that line.
Oh, I can read it.
Can you see it? Okay, what are you noticing about those two floating point numbers?
Only off by a bit.
They're contiguous. Yeah. That's it. They're only off by a bit. I see. Yeah. So, in other words, here's a claim. This number right here is the absolute smallest real number that I can store as a normalized floating point in binary 8. So we call that real min, the smallest floating point number. So what's the absolute smallest normalized floating point number that I can store in MATLAB? 0.25, or the corresponding opposite of 0.25, which is negative 0.25. Why is that the case? Well, let's think about it this way. What are those bits 6 through 4 or 4 through 6 correspond to?
Actual real number.
Not 0, 1, 2, and 3. The exponent, right? So if I have 0, 0, 1, what's the value of that exponent? -2, because 1 minus 3 is -2. And then all the significant fields are 0. What does it mean for all the significant fields to be 0? There's no fraction. So I just have 1.000 times 2 to the -2, which is 2 to the -2, which is 1 over 4, which is 0.25. The moment that I go from this one right here, right there, I'm incrementing by 1. So this is equivalent in way back when of just going to the next integer in my, so like in uint 8, right? In uint 8, these would all be 0, and then the last one would be 0, and if I went up by 1, the last one would turn to 1. It's just that I'm, each individual counting happens within the exponent. So let me ask you this. What do you expect, without looking at it, what do you expect the differences between those two floating point numbers to be? So without looking at the rest of the table. Okay, so let's think about it this way. Yeah, so you're right to say that 2 to the -4 is the significand, but that 2 to the -4 is scaled by what value? 2 to the -2. So that ends up that the differences between those two is 2 to the -4 times 2 to the -2, which is 1 over 64, right? So here's a claim. What do you notice about every single contiguous, like, so if you look at from stage 1 to 2, or row 1, 2, 3, what are you noticing about the differences between each of these rows? You can see it in the actual sum. Kind of a nice table, huh? Yeah, I think that there's an error right here. Oh, I think that should be 2 to the negative 5, right?
Yes.
Because 2 to the negative 6 plus 2 to the negative 6 is 2 to the negative 5, right? So what are you noticing in this exponent field? What are you noticing about the difference between each of the contiguous rows here? To go from one row to the row immediately below it, what do you add? The smallest possible value, which is 0,001 in the significand, but that 0,0001 is scaled by the corresponding value of the exponent. Okay. So what that means is, for that value of the exponent, all of these tick marks are separated by 2 to the negative 6. Okay. Guess what happens when we increment that exponent field by 1? So what would it mean to increment the exponent field by 1? Instead of 0,001, what would it go up to? 0,10. What's the corresponding value of the exponent? The interpreted value of the exponent in that case. Yeah, it would be, u would be 2, right? The unsigned integer string would be 0,10, so the uninterpreted decimal value would be 2, but then what do I do in excess 3? I'm minus 3, so 2 minus 3 is negative 1. So let's take a look at that entry. What are you noticing at that entry? No longer is the significand 0,00 correlating with the value of 0.25, but instead what? 0.5. So literally what we did in that least interesting significand is we multiplied by a value of 2. Why does that make sense? How did you go from the exponent 0,01 to the exponent 0,10? Multiply the corresponding number by 2. So multiplication of binary 8 numbers by powers of 2 does what? Yeah, it changes the exponent with the corresponding power of 2, right? Doesn't actually change the leading or the significant bits. What do you notice about consecutive parts of this table with this exponent field? To go from row 1 to row 2 here, what's the difference? 2 to the negative 5. It's no longer 2 to the negative 6, which it would have been in fixed point, right? One of the things that's really interesting in fixed point is the point is fixed, and so what that means is the delta between any two fixed point numbers must be fixed the moment that I set those parameters. But in floating point arithmetic, what ends up happening is the significant stores precision. The exponent tells me the order of magnitude of that precision. So increasing the exponent also does what? Increases the delta between numbers. So what ends up happening is in that first 0,001 thing, I take the points between 0.25 and then what would 111 be? Well, 111 would be 16, right? So 16 divided by 2 to the 6th? 2 to the 4th divided by 2 to the 6th? Like 0.5, right? So you imagine that the last number, so here's a question, without looking at it, tell me what the last value in the table for where the exponent is 0,01 should be. What's the highest number when my exponent field is 0, 0, 1? I think it should be 0.5 minus 1 over 64. Right? And another way to say that is it's the sum of 0.25 plus 1/4 plus 1/8 plus 1/16 plus 132 plus 164, right? So if I look at the sum there, 1/4 plus 1/8 plus 1/16 plus 162, that number right there is definitely 0.5 minus 164, right? Okay, let me ask you this. What if I increment this number, the exponent field, what if I increment it by 1 and I want to look at the last row when the exponent field is 0, 1, 0? What value will that have? Well, let me ask you this. What's the value of the significand in that? The maximal number in any value of an exponent, the significand will always have ones, right? So in other words, that's going to be like 2 to the 8th plus 2 to the 4th plus 2 to the 1st plus 2 to the 0. But then we scale all those down by the corresponding value of the exponent, right? So first of all, these are all shifted backwards. So the biggest one this would be is 1/2. But then I scale it down by 1 more, so it would be 1/4, right? The minimum value is 0.5, right? Because in normalized, if you have all zeros, your minimum value for the exponent field 2 would be 0.5, no? There it is. So I just keep adding 1/32ths. What would I get up to? One minus 1/32nd, right? And another way to say 1 minus 1/32nd is 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32nd. The moment I hit that 1/32nd, that's going to carry over to the 1 over 2 to 16, which carries over, round up, and I get up to 1, right? Okay. So, I'll let you all play with those. Could you guess where we're going next? Yeah, say it again. Yeah, so what we've just done is talked about what we call binary 8. And I'm actually going to have you all copy this for yourself. What is that? So what does this tell me? Okay, let's go real slow. Total number of bits 8. What's the formal name of that data class? Binary 8. Nickname for that data class? Quarter precision, because for some reason they called binary 32 single precision. So if you divide by 2, if you go from single and divide by 2, what would you call that? Half precision. 32 divided by 2 is 16. If you take half precision and divide by 2, quarter precision. So that's where that name comes from. How many bits in the sign for every floating point number? 1. Number of bits in the exponent. There's an actual really fun problem, which is why do we store exponents in this number of bits? We're not going to cover that this quarter. That's a design problem that's fun to think about. Okay, so in binary 8, how many bits did we store for the sign? 3. And then what do we know about 1 plus 3 and 8? What's left over? 4, right? So if I store 1 for the sign, 3 for the exponent, how many do I have left for the significand? 4. All right, in 16, claim, how many bits for the sign? 1. So in half precision arithmetic, I have 1 bit for the sign, 5 for the exponent, and that leaves 10. And then what we're going to say is, to figure out the excess value, we literally take the formula for this. So if I say all exponents in IEEE 754 format are stored in what? What we're going to call excess K, if we use, I don't even know what I should call this thing, the number of bits for the exponent. I haven't really thought about.
Number of bits for the exponent? Well, I always thought that was significant figures. What's the maximum?
Yeah, but like I need a, I don't want to call it, maybe call it beta. If we use beta bits for the exponent, then the bias looks like this. 2 to the beta minus 1, subtract 1. So let's think about what that means. So let's talk about beta number of bits for the exponent, and then we'll look at what the bias value is. Okay, how many bits do we use for quarter precision? 3. So this means that the bias is going to be 2 to the 3 minus 1 minus 1. 3 minus 1 is 2. 2 squared is 4. 4 minus 1 is 3. What's the value of the bias in binary 8? It's 3. Okay, if I store a number with 5 bits in the exponent, what's the corresponding bias? 2 to the 4 minus 1, which is 15. And then the claim on this, I don't think we're going to get into this quarter. There's some really, really fun numerical analysis that we can do, analyzing what's happening when you add two binary 64 numbers. So if you have two double precision numbers and you do an addition, there's some really interesting things that we can say about where the error happens. There's something called extended precision. So extended precision is above the 64. Internally on a lot of Intel chips, so you all know that that most of these things, yeah, so like this particular one has Intel i5. I don't know what you all have, i7, i3.
I think these people else are actually like Pentiums.
Yeah, that makes sense. So in the portion of the CPU, this computer central processing unit, there's something called an FPU, a floating point unit. And Intel actually does floating point calculations in what they call an 80-bit register. So what will happen is it will download stuff from memory into 80-bit registers. That's called extended precision. That's a long conversation that we're not going to get into today, but it's there for you if you want it, right? I've also seen scientists who do extended precision. So I've seen like binary 128, and I've heard of binary 256, but those are really what I would call specialized application areas. Next time we see each other, can you guess what we're going to do for ourselves, and then next week we'll get into other syntax? What are the native MATLAB data classes that every single number is stored in? Single and double. Okay, so let me do this now. Do you want to start with single or do you want to start with double? You want to start with single, okay. All right, so how many, if I'm thinking about single precision, how many total bits do I have? 32, which means that if I think about the raw bit string, what is the index I'm going to use for the most significant bit? (31). How many total bits are dedicated to the exponent? 8. So this is going to be 30, 29, and it will go down to what? 30, 29, 28, 27, 26, 25, 24, 23, which kind of makes sense because 30 minus 8 is 22 plus 1 is 23, right? Okay, what about these ones? Okay. Leading thing here, what's that called? Sign bit. Okay. How about this? What's that? And we're going to call this biased K. What is the K value here? How many total bits were dedicated to that? 8. So this would be 2 to the 8 minus 1, which is 2 to the 7th minus 1, which is what? 127. So this is excess 127, which means that if I actually want so this implies if I want to get the exponent value from the unsigned exponent code, what do? Subtract K. So this is U minus 127. And another way to say that, what's actually stored in memory? What does this represent? Unsigned. So if I want to calculate the unsigned from the exponent, I just add K. Okay, and then what is this called? What's that thing right there called?
The Mantis.
Yeah.
Make you upset.
Yeah, it doesn't make me upset. It makes me smile, actually. When I learned this from a man that learned it in the 1980s.
Back in the days before calculators,
Yeah.
we had to use logarithms.
Okay. So let's go ahead and write this thing out. What is the corresponding value of y? -1 raised to the sign bit times 1 plus f times 2 to the e. The moment we see a 1 right here, what do we call that? That's called a normalized floating point. What's true about u in order for that to be normalized?
Not be 0.
Yeah. 1, 2, 3, 4, 5, 6, 7, 8. What's the maximum value? All ones, 1, 2, 3, 4, 5, 6, 7. Except here, if U is a string of all zeros, what do we call that? We'll call that subnormal. If U is a string of all ones, what do we call that?
Super. Nan.
Yeah, you can think about it as overflow.
Overflow error.
Yep. In which case we would recast it as a higher. Yeah, and so next time what we do is we'll actually do some of this conversion by hand, and then we'll do some experiments with numerical computation to see how this actually works out. So we've now introduced the theoretical background behind how numbers are stored in MATLAB, and we'll see how that plays out in practice. All right, it is now 11:51. Can we start again at 12:01? I'll have a brief introduction. I plan to do a lot less talking in lab right now. Maybe I'll do 15 minutes, and then the rest of the day is yours to work on the lab that's posted. So I'll see you